We're back in San Francisco and the AGU fall meeting is well underway. Stay tuned. Hello and welcome to day 2 of AGU TV. I'm your host, Juliette Goodrich. The AGU fall meeting brings over 20,000 attendees together to engage in all the latest and greatest science around the world. AGU TV is here to cover it. Today we have exclusive interviews with top newsmakers and we're touring top universities and organizations doing cutting-edge work in science. I'd like to introduce now Dr. Robin Bell. She is the president of AGU. And Dr. Bell, thank you for joining us.
My pleasure to be here talking with you.
I know the main topic, Convergent Science. Why don't you talk about that, what it is?
Well, Convergent Science is where scientists and the scientific community work with communities to address a question. So instead of just being basic discovery science, which we love to do and is really important, but we actually work on addressing a question by working as an interdisciplinary team and with communities.
What are the questions to connect with the audience, with the community, to get people interested?
Okay, one really nice example is that I work in Antarctica and Greenland, and people care about how the ice is melting. But what people really care about is what's going to happen at their shoreline, what's going to happen to their beach. So convergent science is where you take someone like me who worries about how you raise sea level, and we work with communities to understand what's going to happen in the future and how it's going to impact them.
Are you seeing that connect? Is it working?
Oh, we're just about to start a new project where we are actually going to Greenland and working with communities who live up close to the ice sheet. Again, trying to understand if we can better predict what their future is going to look like, but help them design the experiment with us.
And at this conference here, are you seeing that? Are you seeing the lectures and the people talking about it, connecting with the convergent science?
Yes, we are moving that way in AGU. We have an entire section now that's focused on geo-health. So how is it that the changing environment impacts people's health? Whether it's what are the controls on air pollution, or what's the impact on air quality from wildflowers, or maybe even wildfires.
Yeah. So Dr. Bell, you've been president of AGU for a year now. Where is AGU headed?
Well, AGU is in a very special place because we're just 100 years old. So we are about to pivot to the next century of discovery and solutions-based science. So really what we're doing is saying, what have we learned in the last 100 years? 100 years ago, we didn't know how old the Earth was, we didn't know the plates moved, and we didn't know climate change. And now we know that, and we need to inject that knowledge into the future of human on this planet.
True. All right. Well, Dr. Bell, thank you so much. President of AGU, we appreciate your time.
Oh, my pleasure. Thank you.
Joining us now is Dr. Eric Riggs, and he is the EOS Science Advisor for Education. Thank you so much for joining us.
Thank you for inviting me here.
Let's begin with, how does that connect to the education section as Science Advisor?
Sure. So EOS is the science news magazine for the American Geophysical Union. And for each section represented, each content area section within AGU, there is a science advisor to EOS that helps guide EOS's news reporting and other kinds of connection to the community. And so all of us who serve in that role also are on the leadership teams for each of the sections. We're on the executive committees for each section. So that's the connection.
And what are some of the things that the education section is working on?
Well, the education section is brand new. It's first year in existence. Its birthday is at this fall meeting.
Happy birthday.
Thank you very much. And so the leadership of the team, so the president, the incoming president, and the secretary have done a phenomenal job of helping to establish exactly that. There are so many things that are going on with education, because the needs for building out our workforce, the needs for connecting to community, to making the public more scientifically aware of what's going on in the geosciences, all these things go through education and touch education in some ways. So.
Yeah, as science advisor, what is your specific role?
So my specific role is to encourage and also to field proposals from our community. There's a vibrant geoscience education research community, people who do learning and cognitive and educational research on how people understand the geosciences and how we can do that more effectively. So my job is to liaise with those people, find out what's going on, bring it to EOS. Also to connect with the broader science community who are doing really fantastic outreach efforts, and to make sure that they come to EOS, that we can reach out to them with good science writing and get their message out there into the world outside of the geoscience community.
Connecting all aspects of it.
Indeed,
All right.
Absolutely.
Well, Dr. Riggs, I want to thank you for joining us.
Sure, thank you so much.
Spatial Sciences really is the combined theory, practice, and technologies that enable people to address substantive issues through the lens of spatial data, measures, and modeling.
When we think about health issues, when we think about globalization, when we think about these ideas of urbanization, and we think about issues with our environment, all of these big topics leverage the science of where, spatial sciences, in order to assist in solving those problems.
Spatial Sciences Institute was founded in 2010, and it's housed in the Dana and David Dornsythe College of Letters, Arts and Sciences. From the get-go, the vision was that it would be cross-cutting in terms of how it introduced spatial sciences to students and the kinds of research projects and portfolios that we built.
We're an interdisciplinary group of faculty at USC. Really where our mission is at USC is to spatially enable the university, is the way we like to think of it. We bring that interdisciplinary join of computer science and geography into these other disciplines to hopefully ultimately help them transform the world into a better place.
Even within spatial sciences, our faculty are very diverse. We're going to have a political scientist, a human geographer, a biologist, and a geophysicist, all within the same academic unit.
This is an area of danger. My background is in spatial statistics and tectonophysics. I'm a researcher at ESRI, Environmental Systems Research Institute. I'm involved in creating new tools, especially for the spatial statistics team, that a city planner can use, but also a climatologist can use. Spatial machine learning allows us to represent space in a way that generic machine learning methods cannot, so that we can actually understand a simple message, a simple story from terabytes or picobytes of data. I'm interested in studying atmospheric pollution and ocean pollution. In an ideal world, if you see pollution, drop a pin and share that data with everybody, because know that it'll be used by someone at some point. We can actually build that cognitive system for our planet so that we can better our planet faster.
I'm an active duty Army officer for 30 years, and in that life I did a lot of work providing safe and secure communities using some of these very dynamic current technologies in the spatial sciences. I'm working with the folks in the international relations community, the folks in public policy, the folks in political science. We work on projects where we use a lot of the more current technologies in satellite imaging, so small sats as they're often used and termed, and bringing that data, very current, real data of the world, and then from that figuring out what's actually happening on a place of the earth that is not seen by many people. When we think about human rights violations, these are ways of communicating that to the decision makers so that they can make policy or take action.
Some of the work that we're doing here is tracking village burnings in Myanmar as a result of the genocide that started in 2017. The places where these human rights atrocities are happening are data deserts. We don't have any data on them. What we do is take data from these new, really cheap satellites that are able to cover the entire Earth daily.
We aim for our students to be able to contextualize the geographic information and the spatial information and analytics that they gain here to use geographic knowledge to affect change.
We've built a series of academic programs that include us and complementary kinds of training. So at the undergraduate level, we have a geodesign degree that's a collaboration between Spatial Sciences, Public Policy, and the School of Architecture.
Students also have the opportunities through Spatial Sciences to work on research, either through independent research with faculty or through team projects that we have in conjunction with maybe the county.
I was in the geodesign major, and I am now working at an architecture firm downtown. The multidisciplinary nature of the program was a huge asset for me. It helps people make more informed design decisions, it helps craft better project narratives, it helps advocate for better choices when you're presenting to a client.
I'm a scientific applications software engineer in the suborbital radar science and engineering group at JPL. I did the MS in spatial data science program. In the past, people have come to these positions from either a spatial or GIS background, or they've come to it from a computer science background, where in reality they need both skill sets. The spatial data science degree provided me with the perfect skill set to do what I do now.
We want to leave our students with a really good grounding in spatial thinking. We've helped them find the places where they can apply maps and different physical and human data together in an interwoven way. They're in the real estate industry, now they have a much better understanding of location. Or if they're in the public health field, they have a much better understanding of how to trace an epidemic, for example.
When I think of the sort of the grand challenges in the world, it's climate change, species extinctions, freshwater availability, and then the rising inequalities. Spatial Sciences, it has a piece that has to do with theory and a piece that has to do with practice and a piece that has to do with technology. You bring in all of these other complementary fields with their expertise and perspectives on how to address some of these problems. Then we have a hope of making a real difference.
The Water Resources Group at Washington State University is focused on understanding hydrologic systems and bringing innovation and solutions to problems that we see with water quantity and water quality. These are highly tied to the climate change effects we see happening now and into the future and associated land use change. Because these systems that we study are very complex, they involve decision making with humans, we also interact a lot with people who study economics, sociology, and the associated political implications of that. And because of this work, we automatically integrate it back into our own work, and we do a lot of integrated hydrologic modeling with that.
Climate change is impacting the Columbia River Basin. The Columbia River is critical for irrigated agriculture, for hydropower generation, for several fish species that are endangered. Our precipitation is falling primarily during the wintertime as snow, and this stores up in the snowpack and then is released in the summertime for summer water use. And so what we're worried about with climate change is that warming will cause a reduction of the snowpack, and that will therefore reduce summer water availability and cause an increasing frequency and magnitude of droughts. So we're doing quite a bit of research to identify solutions for this problem. With the reduction of snowpack as a storage, we're looking to other types of storage. There is some artificial or reservoir storage in the Columbia River Basin, but it's limited compared to other watersheds. It can only hold about 30% of the mean annual flow in these reservoirs. And so we're looking to other types of storages, and one of those is groundwater as a storage system. The problem is that this needs to be done in a sustainable way.
The focus of my work in the Water Resources Group is to characterize large hydrologic systems. So I'm really interested in understanding how humans are using and impacting groundwater bodies. I use a diversity of tools to do this, from satellite remote sensing to individual citizens monitoring their own groundwater. Ultimately, I'm interested in answering how much water do we have, how much water do we use, and how much water do we need?
Well, I would say that groundwater quality is important, and it goes hand in hand with quantity, because as you are reducing quantity, you start to care more about the quality. And the only way that we can think about quality is by understanding how it actually flows in the subsurface, what kinds of things it's picking up, how it's interacting with different things that are out there. And especially with groundwater, because it's been in the ground for so long, it's got residence time of thousands of years. So whatever has been going on, whatever things that it's been collecting and interacting with, that's what makes the quality important.
Some of the concerns about groundwater contaminants are that they can come from just about anywhere. Depending on what you plan on using the water for determines whether or not something is really a contaminant or whether or not it is just something that's moving with the water. So there are going to be things that are naturally dissolved in the water, like certain types of metals that are in your drinking water that are totally fine, but at high concentrations those can start to become a bit of a problem. The things that we're a little bit more concerned about have to do with what we would call anthropogenic contaminants, and those are ones that humans have put into the environment. So these can include things like fertilizers, these could be fuel additives, these could also be things that are naturally occurring that are stimulated by something that we put in the environment. So bacteria would be one of those.
So many lakes in our region are showing signs of impairment. And it's clear that these lakes in the summertime are almost green with algae and have high vegetation growth. The smaller lakes are showing this earlier than the bigger lakes. And the reasons for it is that many more people are using the lakes, their recreation on the lake and living around the lake, and the lakes are warming due to higher temperatures. The problems that we see with the bigger lakes is that we are probably not understanding that the little lakes are early warning systems for them. We need to understand the causes, and we are doing research on those causes, and one of them is groundwater flow to lakes. Once groundwater is already highly contaminated, it takes a long time to reverse that effect.
My experience working with WSU's Engineers Without Borders has been great. When I was in Panama as a Peace Corps volunteer after graduating from WSU, I was trying to solve a problem in the community. They wanted water year-round, and I didn't see how that could be done with the resources that they had. I thought what they really needed was information about their groundwater resource, but that information wasn't available from any local agency. So over phone conversations and email conversations with Dr. Carl Olson, one of my past professors here at the university, Engineers Without Borders was created, and since then they've been back on 2, soon to be 3 trips to Panama. They've mapped the community. They've been able to see the resources on firsthand. We've installed a solar-powered pump system that serves about 200 people, and we're planning on building a community outreach center in the capital of the reservation I was living in to just keep on going.
I see quite a few challenges, but also opportunities when I look ahead at groundwater work in the future. The biggest challenge is just raising awareness that groundwater is a crucial part of our water cycle and also a crucial part of the water supply that we use every day. I think the more we can help people understand that when you turn on the tap, that water is not just coming from the rivers that we can see, but also the aquifer systems beneath, the better we'll be at planning and managing this resource in the future.
The space industry is growing and exciting because of the exciting discoveries in space, in the outer planets, and especially in exoplanets, that we're not alone in the universe. The Center for Materials of the Universe, part of Arizona State University, is a new center that I'm leading. I'm Alexandra Navratsky, Alex for short. The center's mission is to foster research and collaboration, not just at ASU, but among many institutions, to bring together science and engineering to further our understanding of space, our use of space, and technological advances. My research deals with the stability of materials. In a thermodynamic sense, that's technical. In a practical sense, one wants to know whether materials can form, whether they persist, and what they tell us about the environment, the conditions under which they formed.
My name is Arunima Singh, and I'm an assistant professor in the Department of Physics here at ASU. At the center, I'll be using ab initio simulations to study the possible structures which could exist on exoplanets. These are new conditions. We have extremely hazardous conditions on the exoplanets, extreme temperatures and pressures which can only be probed using computations. But also we can perform control experiments in lab, but they're prohibitively expensive and time consuming. And the computations allow us to map a very huge complex phase space, studying millions of structures. In the next 10 to 20 years, our hope as a group in the center of the materials of the universe is to map the planetary genome. We want to be able to map out the structure and properties of materials which could exist on these exoplanets and in the universe.
I'm Scott Sayers. I'm an assistant professor in the School of Molecular Sciences. So my research lab is an ultra-fast laser lab, which means we use lasers to study chemical reactions and dynamics. We are developing new spectroscopic tools to push the time limits to shorter and shorter timescales, where we're now able to see electron dynamics in their native timescale. And this gives us access to all sorts of new information for materials. In the future, I believe that we're going to be able to make new materials and coatings out of depositing clusters onto a surface. And so instead of having a surface that has a couple of catalytically active sites, we're going to be able to make this entire material chemically active and be able to retain those properties, those unique properties that we observed from the individual cluster sites.
My name is Dan Shem. I'm a mineralogist and I'm a high pressure experimentalist. So I have a lab that studies materials at high pressure and high temperature conditions of the Earth interior and other planets. So planetary interiors are one of the hardest regions to understand because we cannot get that data directly. I simulate the pressure temperature conditions of the deep interior in the lab. For the next 10 or 20 years, I will enjoy studying a very wide pressure temperature range, very wide compositional range, to be able to understand the planets that we never have thought about before.
My name is Joseph O'Rourke. I am a planetary scientist, and my research focuses on phenomena that originate deep within the interiors of planets. My research is exciting because it focuses on big picture questions about Earth and other planets in our solar system and beyond. Why does Earth have plate tectonics? Why does Earth have a magnetic field? These large-scale planetary processes are essential to understanding why our surface is habitable. So we are entering a new era of planetary exploration. Most of NASA's past spacecraft missions have focused on the most easily observable parts of planets, their surfaces and their atmospheres. But the new generation of NASA missions is focused on collecting data about the interiors of planets. The NASA InSight mission is probing the interior of Mars. The NASA Psyche mission, led by ASU, is going to the remnant core of an ancient protoplanet. And so we are starting to gather new data about the interiors of planets, which makes understanding the properties of materials even more of a pressing need.
I'm Hillary Ellen Hartnett, and I'm Associate Professor in the School of Earth and Space Exploration and the School of Molecular Sciences. I'm a geochemist. I also answer to oceanographer and astrobiologist, but my work is to understand carbon and nitrogen cycling on the Earth, and in particular, I'm interested in how minerals catalyze organic reactions in Earth systems. The collaboration between material scientists, mineral physicists, and geochemists can explore the conditions and the chemical properties that might be present on exoplanets. Nobody thinks that organic chemists will be able to tell us something about pH, or temperature, or redox chemistry for a planet around another star, but I think we're going to be able to do that. The Center for the Materials of the Universe has nothing less than the vision of understanding the universe. We envision that the connections with material scientists and geochemists and even astrophysicists is going to allow us to think about new, creative, interdisciplinary ways to explore planets that we can't go to yet.
So we hope to grow, we hope to thrive.
Joining us now is Dr. John Morse, and he is president of Astronautics. And thank you for joining us.
Oh, pleased to be here.
Let's talk about Astronautics. Tell me about it.
Astronautics is a startup that wants to do space science as a data service. And so it's a lot like the companies that already look at the Earth and accumulate data, and then scientists are able to buy data either through NASA or NOAA or one of the space agencies or from other sources of funds in order to do their research. And what Astronautics is trying to do is accelerate the pace of discovery by offering more lower cost options for data to be taken.
I understand that you're part of a panel talking about new access to space. Tell us about that.
So we have a lot of launch vehicle companies, for example, that are getting payloads into space for a fraction of the cost that it used to take in order to send an important scientific payload. And then you have companies that are building remote sensing type of platforms that take pictures of the Earth, but we want to use those kinds of infrastructure in order to study the cosmos. And then we have lander companies. We have 14 companies in the so-called Commercial Lunar Payload Services program at NASA. And these are companies, some of which you've heard of, like Lockheed Martin or SpaceX or Blue Origin, and then some new companies which are trying to innovate in the way they get payloads to the lunar surface. And this, during the next 5 years, this is going to be the way a lot of science is going to get done, is by buying services, transportation services or data services in order to accelerate discovery.
How do you get scientists involved?
So as a data service company who is interested in accelerating scientific discovery, we actually are what's called a public benefit corporation, and we have a public benefit statement that says we want to accelerate Earth and space science discovery. And that allows us to incorporate scientific needs into our business model. And where do you get scientific needs and requirements but from scientists? And so right now, scientists could go on our website at astronautics.com, and there's a panel there you can click on to send us your information and your interest in, for example, a dedicated solar system space telescope mission. That would be a small observatory to start with, but we want to grow the capabilities over time. So scientists' interaction with Astronautics is at the core of what we're going to do.
All right, Dr. Morse, thank you so much.
My pleasure. Thank you.
Joining me now, Dr. Melinda Webster and Dr. Anna Gold, and thank you so much. And first, Melinda, I want to mention that you are a sea ice geophysicist with the University of Alaska Fairbanks, and Dr. Gold, Outreach and Education Director at Ceres. Let's begin first talking about Mosaic. Why don't we start with you, Dr. Gold, and tell us what's happening?
Yeah. Mosaic is an Arctic expedition. There is, the acronym stands for Multidisciplinary Drifting Observatory of the Study of the Arctic Climate, which means there's a central observatory, which is a ship, an icebreaker that's frozen in the Arctic Ocean. That happened in September at the sea ice minimum. And it's drifting with the transpolar drift and collecting, and there's scientists over the course of the year. There's up to 600 scientists involved in this expedition. They cycle in and out with different icebreakers or fixed-wing airplanes throughout the year, and they're collecting data on the Arctic climate through an entire season.
I know you've been on the expedition and you will be going on it. And as a geophysicist, why don't you talk about the science behind these expeditions?
Yeah, this is a really exciting opportunity for the science because it's not just a snapshot of capturing what's happening in the atmosphere, or the sea ice, or the ocean. We're staying there for an entire year, seeing how this seasons cycle throughout the year. And we're going to be taking measurements of the ice, of the ocean, of the atmosphere, of the marine ecosystem. All these are intimately linked together. So when one thing's changing, like the ice moves, it affects everything else. It's a cascading effect. So this is a pretty huge effort. There are over 600 scientists involved in this. And it's really going to revamp our understanding of climate change and the changes that are going on in the new Arctic.
What challenges did you face? And then I'm going to ask you what challenges scientists face, but what did you face when you were on that expedition?
So I was on the first leg of the expedition where actually 2 icebreakers went out together. This drifting observatory, polar stern going up. It's an AVI-led expedition, but it's heavily funded by the National Science Foundation and Department of Energy and NASA and NOAA from the U.S. for the U.S. contributions. But so we went out, and I was on the Russian icebreaker that supplied and helped with the setup. And one of the big challenges for this initial leg was finding the correct ice flow. So we left Tromsø in northern Norway and went out into the ocean, and we're looking for sea ice, an ice flow that's thick enough to be having all these networks of stations that are set up on the ice around the around the icebreaker. And the ice is very thin, thinner than it has been in the previous years. And so it was a challenge to find the right ice flow at the right location where the transpolar drift would actually not spit out the ship too early and would really allow for a drift for an entire year.
Wow. So knowing this and knowing what's ahead during your expedition, what challenges do you face as a scientist?
Yeah, there are a lot of challenges that we face. The ice is a very dynamic medium, so it moves around with the wind and ocean currents, which also means that it breaks, it cracks, and things move around a lot. So how the instruments are distributed on the ground or on the sea ice are going to change. They've already changed. There was a big storm that happened in November, and it shifted the ice camp and split it apart, and it shifted it by 300 to 500 meters, and that's pretty important when it shears cables that are supplying energy to our instrumentation. So we have to be adaptable. We have to learn to adapt our plans and be ready for that, which is challenging, but it's possible.
So what is the outcome that you hope to achieve with Mosaic?
Right, we're spending a lot of time and energy taking all these measurements. And what it's really important to take those for is to firstly assess models and to find ways to improve how models represent the real world. And this is really about improving our predictive capability. We want to know what's going to happen in the future with climate change and what are those effects on weather, on ecosystems, and society. So with this information, we'll really be able to leap forward our ability to predict what's going to happen.
Thank you so much. Fascinating, and best of luck and on your expedition. Appreciate it. Thank you.
The Sierra Nevada is really in an unsustainable state. We know that it's burning. Every year we get wildfires that consume tens to hundreds of thousands of acres. Over 100 million trees that suffered mortality, tree deaths during the last most recent drought. Our institute addresses resource management challenges in the region and also enables our faculty and students to use the region as a natural laboratory for research.
My research is looking at the water balance of the Sierra Nevada. I'm very interested in knowing what California's water supply is going to be. So we're very interested when precipitation comes down, either as snow or as rain, how much of that actually ends up in the river. We can make better decisions if we understand the system well. And the problem with working up in the mountains is that it's very difficult to get measurements. And we've been sprinkling devices such as wireless sensor network around the Sierra Nevada because we can actually measure snow depth using this instrument. We tend to have on it, we radio out the signal, so we have it in real time. We also have information, other measurements such as relative humidity and temperature, so we can actually start doing energy balance calculations as well.
I'm a plant biologist, and I'm interested in the way that plants, and particularly trees, are responding to environmental change. So climate has already shifted a good bit in California since the early 20th century. Most of the state has gotten hotter. The northern part of the state is getting more precipitation than it used to. The southern part is getting less. And all of that can have some profound impacts on tree populations. As many people know, during the recent drought in 2012 to 2016, there was a lot of tree mortality because this drought was one of the most severe that's been seen in the last 1,000 1,000 years. But those types of droughts are expected to become more common in the future, and so those types of events may repeat. And even when you don't get these dramatic mortality events, the increases in temperature and drought have been leading to higher mortality just on an average year in both adults and seedling trees in many areas of the West. And that, coupled with the increase in wildfires from drier conditions, raises a lot of concerns that forests may not be able to regenerate themselves, that the young trees will not be able to grow up fast enough to replace older trees that are dying. And that, of course, can have a lot of implications for carbon storage in these forests, for habitat, and for any other uses of these forest lands. So knowing how this variation is distributed in space, as well as what genetic variants are causing these differences between individuals, might allow us to better choose seed sources when we're reforesting after events like wildfires that will be better able to tolerate the conditions that we're going to see in the future.
In my lab, we study soil organic matter dynamics, which is to say that we study the biogeochemical cycles of carbon, nitrogen, and phosphorus, in particular how those cycles are affected by physical perturbations in the environment, such as erosion, fire, or climate change, and focus in particular on how these changes then affect the ability of the soil system to store and stabilize carbon and organic matter. One of the most important challenges facing humanity right now is soil degradation. And soil use and degradation just in the last 200 years or so has released 12 times more carbon to the atmosphere compared to the rate at which we're now annually releasing carbon. Some of the best ways that we can improve are reduced tillage, reduce disturbance from agricultural practices overall, reducing excessive use of agricultural chemicals, stopping deforestation, and putting back forests whenever possible, promoting planting of deep-rooted perennial plants. All of those are proven methods that we've shown over the years that they can increase the amount of carbon stored in soil.
I look at the historical experience of wildfire and what's driven extreme wildfires in the recent decades. And that includes changes in temperature, changes in precipitation, changes in snowmelt timing, changes in season length. And then we use that information to understand how fire may have responded in the past to climate and how it may respond in the future to climate. So best case for California is that we can aggressively manage our forests to make them much more resilient to climate change and get the fire out of the forest canopy and more often at the surface at lower intensity so the trees survive, maintain a stable carbon reservoir for the next century, and sort of support both adaptation and mitigation. I think the thing that's important for people to keep in mind is not that they should despair and throw up their hands and say nothing can be done. It's that there are things that we don't know how to change. But there are things that we can change. So we can't really dramatically affect the climate change that we're going to experience in the next couple to few decades. But we can dramatically change the prognosis for our children.
I'm very happy to have such a great group of faculty here in the Sierra Nevada Research Institute. And we can do great things for restoring the Sierra Nevada and bringing more sustainability to our region.
I work on issues around water sustainability because fresh water is crucial for drinking, growing food, generating energy, and almost every other aspect in our modern life.
Future H2O is a research initiative at Arizona State University. It was born out of the White House Water Summit in 2015. The goal of Future H2O is to change the conversation about water from one about scarcity and risk to one about opportunity.
Sustainable water practices, I think, are important for industry for a variety of reasons. Number one, all companies want to grow. In order to do that, we have to use the natural resources that we're given wisely and conservatively. The second reason, I think, is that one of the things we have learned in our journey in sustainability is that we can do a lot by ourselves, but we can do even more with others. And by bringing in other partners, we can find more innovative ways to accomplish our goals.
Levi Strauss came to us and said, hey, we do a lot of work in Pakistan. It's where we grow and manufacture blue jeans. And we want to make a difference in terms of water sustainability there. How can you help us do that? And so we took the approach of saying, well, Levi Strauss is already a leader within the four walls of their factories. Let's start thinking about how we can make a bigger impact outside the four walls.
So the area around Lahore in upper Pakistan depends largely on groundwater for usage for industrial uses. And the reality is that the usage of groundwater is unsustainable there. The water table is dropping by 1 meter every year. And so that's why we've teamed up with our partners at Future H2O, Earth Genome, and World Wildlife Fund to create an innovative science-based tool that uses simple maps to show where the risk hotspots are at both kind of a watershed level and a local level.
Basin is a web-based basin assessment intervention tool. Basin is built based on the first 3D high-resolution basin-scale groundwater flow model for the entire Indus River Basin. With Basin, we can simulate groundwater dynamics, reveal the influence of climate change and human activities on water budget. With its help, we can strategically allocate groundwater recharge to improve the basin health.
Through Basin, we really pulled together what I consider the key ingredients to a successful partnership. You have the science, the stakeholders, and the solution, and hopefully brought up to a scale that really moves the needle on the ground.
I go to water meetings and a water meeting circuit every year, and one of the themes that's often discussed is that the leadership in water is about to retire. One of the things that we think we can do at Future H2O is train that next leadership to be more savvy about how to use data to make better decisions.
So the Global Water Classroom is actually one of Future H2O Water Education's first projects that we completed. So in this course, students learn about topics as diverse as the water cycle on Earth and within living organisms, the role that water plays within religion, and how big data presents enormous opportunity to improve water sustainability.
We see the sustainability space as a non-competitive space. And so by looking broader at the issue and bringing in multiple stakeholders, we can collectively achieve greater results at a lower cost.
One thing that I think would be a very interesting model to explore is the idea of companies who supply and buy from each other to work together. So, for example, Intel might use filter products that Dow makes. They might sell Coca-Cola products on their campus. That's a supply chain, all of which needs water, all of which could be co-located in a similar basin, and all of whom could collaborate to have a bigger impact.
We know that talking about it is not enough. We know that setting targets, and that alone is not enough. We need to do more than that, and so that's why we really set our sights on changing the whole apparel industry by open sourcing our programs and encouraging industries to follow in our footsteps.
By engaging the private sector through partnerships with different NGOs, we're starting to create science that shows the future and shows a better future.
I think once people realize the gravity of our situation in terms of climate change and environmental change, they might feel like we're doomed, like this is very stressful, and they can feel a sense of despair. And this is not what we are teaching our students here. We're teaching that there's a way out of this. It requires a massive investment from our society. It requires everyone to participate, but there's a way out.
One of the things that makes this department so unique and a leader is that we bring together people who have different areas of expertise. It's very, very interdisciplinary.
I think we have outstanding scholars in our department. That goes back to the time when Ralph Cicerone formed this department and really picked the top experts in the country in these kind of topics. And I think we kept that legacy to work closely together with a common goal for our students and for our research.
So I'm an oceanographer. I study photosynthesis in the ocean and biogeochemical cycles. which is basically looking at how climatological changes to the Earth system affect phytoplankton populations. And those are basically the tiny microscopic plants that live in the ocean and form the base of the marine food web. My group is one of the most diverse, and it's something that I'm really proud of. The fact that everybody's bringing a different set of tools to the table really brightens up the research and explores new avenues that I wouldn't be able to come up with on my own.
I work a lot on the risks and vulnerabilities of human systems to global environmental changes and trying to find scalable solutions to mitigate those risks.
Wildfires are really interdisciplinary. This department has a really long history of studying fires, and in our laboratory we're studying global fires across the whole Earth system using satellite data.
In September, we published a paper trying to predict the final size of a fire from the time that it ignites. This type of prediction is really important, especially in areas that are responding to strong trends in climate.
So Shane was able to predict which fires grow really large, and that's important because then in a situation where there are a lot of fires on the landscape, the fire managers can triage the problem and select certain fires to limit their damages to ecosystems and keep carbon inside ecosystems.
2019 was a very special year. The Amazon was in the news. Our research group gave almost 200 interviews about what was happening in the Amazon in 2019. And the main problem was that there's an increase in deforestation in the region. And so Brazil pretty much created the biggest bonfire for the past 10 years in the region by burning all these forests that are clear-cut.
One place where I've realized turbulence really matters is over the Amazon rainforests. Working with ecophysiologists in the department here, I've come to appreciate that the way the physiology of the forest adapts to high CO2 actually changes the energy balance of the surface in ways that spark turbulence feedbacks. So that's opening up new frontier questions at the interface of our disciplines that I didn't imagine would happen, but I really like that about ESS.
My name is Murat Aydin. I work with ice cores from polar ice sheets. And we talk about atmospheric CO2 changes, right? We know the last 100 years have been highly unusual. And the reason why we know that is directly linked to the ice core trace gas research that has been done.
I study water resources on land and look at how the water storage on land is changed, and that's important because both the ice sheet, has impact because it's going to raise sea level and it's going to impact on the population that live in the coastal area. And water storage availability is a big deal. It's very important, it's a big impact.
We've seen over the past decades that many glaciers around the coast of Greenland and Antarctica have been thinning, retreating, and their flow have been accelerating, discharging more icebergs into the ocean than before. And we first need to identify what the driver of change is, and what we can use numerical models to determine whether it's the ocean, whether it's changes in the atmosphere circulation, whether it's the topography underneath the ice that's making the ice less or more stable depending on where we are.
One of the main data sets that I use is the one from the GRACE mission. It's a satellite mission. It measures the gravity field of the Earth. It means that it weighs the Earth every 30 days and we see what changes from one month to the other. And I think it provides a unique information about the ice sheet. And it's the first time that we are able to measure the total water storage, also including groundwater in remote region as well.
Well, part of what we do is educate this next generation of students, and they're supposed to spread the word, they're supposed to spread the knowledge. We're very proactive also in outreach and social media.
I sort of started climate communications through social media, and I specialize in sort of visualizing climate data through easier to understand graphics. It's not just the advantage of communicating the work, but it's also that you're learning about your own science and how people interpret your work. And I think it's extremely valuable and been very beneficial for my graduate studies.
I've worked at a number of institutions, and I can honestly say that UCI is the most friendly, receptive, inclusive environment I've ever been in, both in terms of the faculty and the students.
We really try to create a community and then provide everybody with what they need to succeed. And having a diverse place, it really helps to have different ideas. We really believe in that.
I really feel like our entire discipline is moving in the direction of merging what we know about the physical sciences with the solutions. Engineers have been doing this for a long time, but engineers tend to focus on pretty small scales, whereas we're thinking about it globally. Humans are by now an undeniable part of the Earth system, and that's where we fit.
Joining us now is Sherry Goodman, and she is Senior Strategist, Center for Climate and Security. And thanks so much for joining us.
It's a pleasure to be here.
Thank you. Let's talk about the effects of climate change and its effect on national security.
Absolutely. Climate change is a threat multiplier on national security. It magnifies, amplifies, if you will, all the other threats that we face around the globe. We see major power competition opening up in the Arctic as it melts, sea ice retreats, temperatures warm, permafrost collapses. Russia, China, and the US are all building and expanding their capabilities to operate in a melting Arctic. We see drought conditions amplified across much of the equatorial regions of the planet, in Africa in particular, and the Middle East. We see people facing increasing food and water insecurity from drought conditions, now migrating and fleeing and also becoming vulnerable to terrorist and extremist groups. Those are just two of the many examples in the way climate change is affecting our national security and homeland security.
What are some of the political concerns regarding climate change?
Well, the main concern is that we need to mobilize and act now. Because we're, fast approaching a precipice where we won't be able to pull back, and where the conditions are going to become so extreme that we're really leaving our children a different world than the one we live in today.
Yeah, and talking about our children, what are some of the things that we can teach and address in terms of the threat of climate change moving forward?
Well, we can teach people to understand and assess the impacts, to take the science that's here at AGU and translate it into assessment and action. That's a continuum, a process that we need to take the science and translate it into action today to make our societies, our communities, and individuals more resilient to climate impacts.
All right. Thank you so much for joining us.
Thank you.
Thank you. That's it for today, but we'll be back each day of the meeting with more exclusive material. See you tomorrow, AGU.